Okay, so let's start with the concepts that we have been proposing. So essentially, we say in the last class yesterday, we said that the form of an exact wave function can be written in terms of Slater determinants formed out of a basis. So first, let me again explain that my bases are the basis of spin orbitals, which I call chi I. Okay. So these are my bases of spin orbitals. So these are basically one particle functions. So that is the first thing. So, and spin orbital, so they are functions of spin and space part. And I deliberately choose this as orthonormalized. So that is of course the choice that is very convenient, which essentially means that any two chi I and chi j, if I integrate with chi I star chi j, if I integrate, the result is a Kronecker delta delta I j. Okay. So that is the meaning of orthonormalization. So I start with a basis of spin orbital, which are basically one electron functions. Let us say that I have a basis, my basis is m dimensional. So let us not worry about completeness of the basis, because we have already discussed yesterday that completeness requires infinite dimension. It is very often not doable. So let us assume that it is m dimensional, where m is sufficiently large as possible, and this is where computer will play a very important role. So when you actually write these quantum chemistry programs, you know that your basis, different bases you use, and the larger the basis, usually you should get a better result. So the reason is very clear. Obviously, m should be much larger than n. Typically, m should be much larger than n, where n is the number of electrons. So n is the number of electron, m is the basis. So these are one particle basis. Then we construct Slater determinants, okay, which are n particle, n dimensional. So Slater determinants of n particle or n electron, okay, using this m basis. Correct. These Slater determinants, they act as a basis for the n particle wave function. Or n electron wave function. Just as your spin orbitals are basis for one particle wave function, any one particle function can be expanded in terms of this basis. These determinants now become the basis for the n electron wave function. Okay. What are the determinants that you can compute? Total number that you can calculate is MCN. Okay. And then what I can do is to write my n electron wave function, let us say psi 0 for the n electron eigenstate or whatever, as a linear combination of all these MCN determinants. Okay. So that is what I mentioned in the previous thing, that you can do like chi I, chi j, chi k, etc., where I less than j, less than k, less than l, and you can have the coefficient d, I, j, k, l, etc. Okay. So each of these functions go up to m, because these are the one particle functions, and if I order, I showed in the last class, if I order them in this manner, you will generate MCN determinants. So I am only taking the combinations. All right. This is now an exact form, full form of the wave function in this m basis. So provided m is exact, this will become exact. Okay. provided m is large enough, not exact, but large enough to be accepted as exact, this is sufficiently good to be accepted as an exact wave function. So, this is now limited only by how good is the m dimensional basis as far as exactness is concerned. This function, if you include all, is what I call full CI in, now I will specifically write full CI in m dimensional basis. So, then I make my point very clear that it is not necessarily exact, but it is a full CI function in m dimensional basis, and as m goes to infinity, this full CI function psi naught goes to exact wave function. Is it clear? This by itself is a full CI. You need not call it exact, we can just say full configuration interaction, which means full essentially means that I have taken all MCN determinants within this basis. So, I call it m dimensional basis, and then of course, I can keep on pushing this value of m as large as possible. I am making this full CI function as exact as possible towards exactness, and eventually if this reaches near completion, then it is an exact function. So, this is what they say is a CBS limit, complete basis set limit. Essentially, it means that m cannot be infinity, but m is sufficiently large that it is almost complete. And if I now take all the CI functions, then of course, it is an exact function. All right. So, we will of course not worry about this, how to, of course, you have to see how to get the coefficients, what is the energy. So, all that will come back later when you discuss the full CI wave function or CI wave method. At this point, I just wanted to mention that even if the Hamiltonian is interacting, there is a form of an exact wave function, which is possible. Of course, if Hamiltonian is non-interacting, a single determinant, any of these determinants should be an exact function, in fact, provided they are eigenfunctions of the one particle operator. So, by clever choice of basis, I can make all the determinants to be exact function for a non-interacting Hamiltonian. The only clever choice should be that these bases must be an eigenfunction of the one particle operator. Is it clear? Then it is automatic. One of them would be ground state, others will be excited states in that case. But the point that I am saying that even for a interacting Hamiltonian, using these determinants built out of these bases, I can make an exact wave function, and here again depending on the energy, one of these will be ground, excited states, etc. So, how will a ground state be different from an excited state? It will be exactly similar form, these coefficients will be different. So, a ground state wave function will have one set of coefficients, and another excited state will have another set of coefficients, and so on. So, these coefficients will distinguish from the ground to excited states in this case. Okay. So, I think this is very important. Then we ask the question, and that was the question that we will actually go into, and that is a part of the Hartree-Fock theory, is that can I identify among them one determinant which is the best. Now, when I ask this question, I have to also bring the consideration of the basis immediately, because if you give me a basis and then say within this basis find out which determinant is the best, that is one type of question. The second question can be change the basis and find out which determinant is the best, which single determinant. That is exactly the question that I am asking, the latter question. So, that means given in some basis, can I find one determinant which is the best in terms of energy, all right. So, that is the question that we will ask. So, we will have full liberty to change the basis sets, such that we identify one determinant within the new basis which will give the best energy. Okay. The best energy would be defined by what is called the variational method. So, I just want to digress here onto a variational method, and then we will come back to the Hartree-Fock method. There are a lot of other technical things that we have to do, as I said, but right now we will go ahead with the variation method. All right. Before I do this, I will quickly go through the variation method. Since most of you have done it, I will not spend a lot of time, but I will try to do it, because in the last class, I think in the 4 to 5, we have taken about three lectures on the various, 3 to even more, I think 3 to 4 lectures on variational method alone. All right. There are many parts to the variation method. I mean, again, those who want to read variation method, I must, I referred it before, I must refer again the book by Epstein, The Variation Method in Quantum Chemistry. There's a fantastic book by Saul T. Epstein. I think this book is downloadable. I'm not sure, but I have not found any better textbook on the variation method. If you can go through 1 or 2 chapters, first couple of chapters, that may be enough. No, but this book is quite heavy. So I refer because this is one of the textbooks which puts variation method in a very systematic manner. All right. So the first part of the variation method is the following, that if I construct an expectation value using some set of trial function, so I call these E tilde, where all these tildes stand for trial. Okay. So my eigenfunction is trial function, energy is of course trial, and then if I vary, if this psi tilde is varied over the entire space, note that this entire space should not be confused with the m-dimensional basis or completeness of basis, because this is a n particle function. I am writing variation method in general. So over the entire n-dimensional space, okay, whatever the n-dimensional space mean, this is very often called the Hilbert space. Okay, I am not going to use this terminology. Then these stationary points, if you keep on varying, then you will have certain points where E tilde is stationary. So the stationarities of E tilde correspond to the eigen solutions of H. This is actually a very powerful method. Again, I am stating without proof that if I keep on varying this psi tilde, so this is a variation, obviously means I keep on changing, my E tilde will change with psi tilde, and there are certain points where there will be a stationarity. What a stationarity means? The first derivative will become 0. First derivative will become 0. It can be maxima, it can be minima, remember. All these stationarities correspond to an eigen solution of H, which means the E tilde will be eigenvalue at that point, whatever is E tilde, whatever is psi tilde at that point will become eigenfunction. Okay? So all of them will become eigen solutions. If you look at this theorem, the theorem actually completely solves the problem, because that is what I want to do. I want to solve H psi equal to E psi, and the theorem says how to do it. Correct? So it is a very powerful theorem, which is very often called the Euler variation method. In fact, Euler is a mathematician. So for mathematicians, eigenvalue problem is a very important problem, and Euler came up with how to solve the eigenvalue equation. In fact, this is one recipe for solving the eigenvalue equation of anything, except that this is extremely difficult to implement, because there is a very important part here is entire n-dimensional Hilbert space. So you have to span a complete Hilbert space, then only you can check these stationarities. If you don't span, then these stationarities need not correspond to the eigensolutions. So if you only restrict your variation within a subspace, okay, then whatever stationarities you get, they need not be eigensolutions. So the proof actually requires this entire thing, and again it may be mathematically very nice, but physically almost impossible to implement, just like the completeness of basis. So although this theorem is very elegant, and I repeat that the Euler variation is an extremely elegant theorem which is never taught in chemistry or even physics, I don't know. It is not practically feasible, and that is probably the reason it is never taught. But I believe this is a very nice theorem. Actually in 425 we had proved it, the entire theorem. I am not going to do this, but I am just going to make a statement here. There is a converse to the theorem, and the converse is also interesting. If H psi is equal to E psi, that is, if I know the solution of this eigenvalue problem, then the psi corresponds to not only psi, then the psi and E correspond to the stationarities of these functional psi h psi by psi psi. So, this is a converse theorem that not only the stationary points of these correspond to an eigen solution, all eigen solutions also correspond to the stationarities. So, it is both ways. So, that is very interesting. That means you do not miss anything. Okay? So, both can be proved very easily. By using these, one can prove that by any change of first order change in del psi, the first order change in energy will become 0, or conversely if the first order energy change is 0, you get h psi equal to E psi. Okay, so, that is a converse. I am not going to make the proof here in this class. I had done that in 425, but I think for this class this statement is important. Okay. So, I hope you understand the meaning of this, that I keep on changing psi, I look at energy, and then let us say that I have a very simple plot of energy versus psi. So, E tilde versus psi tilde, then there would be some kind of curve. Let us say I am very simple, a very simplistic thing I am discussing, then these are the stationary points. So, this is my psi tilde, this is my E tilde. So, each of them is an eigenstate of the Hamiltonian, and of course, the lowest of them is the ground state. That is obvious. So, it is just a curve which is just simply done. It is one 2-dimensional, but this is what we mean by stationarity. You can keep on changing psi tilde, you will get different E tilde and see where are the stationary points. But if you can do that over the entire space, then only this theorem is valid. Okay? And that essentially kills the practical utility of the theorem, however elegant the theorem is. Okay? Then we come to the next, which is the content of the all practical applications of variation method, and that is that was developed by Rayleigh and Ritz. It is called the Rayleigh-Ritz variation method. So, it is developed by Rayleigh-Ritz. It is called the Rayleigh-Ritz variation method. This says that if you take any psi tilde, arbitrary psi tilde, okay, and then calculate this expectation value, okay, here I am not varying. The statement says for any arbitrary psi tilde, if I calculate the expectation value, this is always greater than or equal to the exact ground state energy. This E naught is exact ground state energy. Okay. So, for example, here let me write this as H psi I equal to E I psi I, and E0 less than equal to E1 less than equal to, etc. So, I think it is very clear that the E0 is the ground state. So, it says that whatever for any arbitrary psi tilde, including this, whatever I did, it is always greater than equal to E naught. There is no confusion with this because there is an equal to. So, one of those points which is stationary will be actually E naught. We now know this. If I do an entire search over the Hilbert space, then one of those points would be E naught. But this theorem is much more practical because it says that even if you do not search over the entire Hilbert space, you just take any arbitrary function, this is always equal to at least greater or equal to the E naught, but only E naught, no reference to other states. Okay? This theorem makes it much more easy to apply, because now I do not have to search. Where is the concept of variation here? The variation now comes in a different way. For all arbitrary function, this is greater than equal to E naught. So, if I keep on varying over whatever space I want to vary, the minimum of them would be the closest to E naught, right. So, if there is a sense of variation, minimum of this will be the closest to E naught, quite clearly, because everything that I do is greater than E naught. So, the among whatever variation I have done, the minimum of them would be closest to E naught. How close? Of course, I can't tell. That depends on how good you are in varying. If your variation space is pretty bad, still within that space minimum would be the closest, but you are pretty off. If you do a good variation, your space will come down. So, for example, if this is your E naught, I can have a space of variation which is bound by this. So, this is the best. I can have another space which is bound by this, then this is the best. Okay. In each case, of course, E naught lies lower than whatever I do, and in principle, if I do a complete variation, then of course there will be one minima which will touch this, E naught touch. If I do a complete variation, as I said, so there is no difference from the Euler. But even if I can't do, I know at least whatever I have done within that I can pick up the best terms of ground state. So this is called the upper bound property of E naught. Okay. So E naught is always bounded, or E naught is always lower than that expectation value, lower or equal. Okay. So this is a very, very powerful method, and now I can actually do a variation on whatever space I am doing and then pick up the best one, which is basically the minimum. So there is a minimization. This theorem again, can be proved. So what essentially is telling that if I have a Hamiltonian, and just in case this psi and this psi conflicts, I am going to use a different symbol for the eigenfunction or exact eigenfunction. So let us call it H phi I equal to E I phi I. Okay. So these phi i's are eigenfunctions of the Hamiltonian. Obviously, they form a complete basis, all the eigenfunctions, although I do not know them, but in principle they exist. So a complete basis exists, and they are also orthonormal because they are eigenfunctions of Hermitian operator, correct. So now I have a situation where any of the psi tilde can be expanded in terms of this basis. So I equal to whatever 0. So 0 is part of the number. So 0, 1, 2, 3, etc. Okay, the entire basis. Note that the basis that we were talking chi was a basis of spin orbitals, which is one particle basis. These are actually n particle basis. So this can be our determinants. I told you in the full form of Ci that the determinants form a basis for the n particle. So they can be like determinant, these phi i's. Okay, but actually they won't be determinant simply because the determinant cannot be an eigenfunction of H. But like that, an n particle function, maybe a linear combination of determinants, whatever. I don't care what they are. I don't need to know them. These are the functions which are eigenfunctions of the Hamiltonian, and my any psi tilde that I construct can be written as a linear combination of the eigenfunction. Please note that I am specifically writing from I equal to 0. So that is just a symbol change. So then I calculate psi tilde H psi tilde. Okay. Let me also assume that, and this is without any loss of generality, I can do that the psi tilde is normalized to unity. What would that mean is that the sum over I modulus Ci square would be equal to 1. I hope all of you can easily show this, right, because psi tilde is 1. So if you just expand, these are the orthonormal sets, you can see that Ci star Cj phi j integral, which is delta ij, so it will become Ci star Ci equal to 1. So it is very easy to show this mod Ci square. Please make sure that these are very elementary algebra which you can do it, in which case I do not need to write the denominator. That is the only reason I am assuming that this is normalized unity, but I will remember that this coefficient square sum is equal to 1. I have to remember this, that is the condition. So what would be this now? You expand psi tilde on both left and the right hand side with this expansion. So let us use for the left one a dummy variable j, for the right one a dummy variable I, and expand this as phi j H phi I Cj star Ci. Correct? It is very easy to do this. Cj star phi j star H Ci phi I, Ci phi I. Okay? So I am again using the Dirac notation to do the integral. This integral can be trivially calculated. Why? Because all these phi i's and phi j's are eigenfunction of the Hamiltonian with eigenvalue Ei. So it is very easy. For example, H acting on phi I gives you Ei phi I. So Ei comes out, phi I phi j is delta ij. So, I can easily write this as sum over ij ei Cj star Ci into delta ij. Is it clear? Ei will come because of this, and then phi j phi I will give me this delta ij Cj star Ci remains. So, now that delta ij is there, I can write it as a sum over I ei mod Ci square. Okay, because now j is equal to I. So, j must be equal to I. So, Ci star Ci is mod Ci square, ei delta ij is 1, and I not equal to j, it is 0. So, I do not have to bother. Note again that this is an expansion over a complete basis. Okay, I do not know ei, I do not know phi, but this is a in principle expansion. So, I do not need to know, okay, just to prove. So, then we come to this situation where I now know that the psi tilde is sum over I ei Ci square. Now, I do the same thing for E naught. So, I am basically comparing this part with this part. Okay. Now, I compare with E naught, and I write E naught as E naught times sum over I mod Ci square. Please note that this quantity is 1. So, I have a right to multiply E naught by 1. So, I just did E naught times mod Ci square, and then I expand this E naught times mod C0 square plus E naught times mod C1 square and so on, plus E naught times mod C2 square and so on. Is it clear? I just expand this. Okay, and then compare with this part. If you expand this part similarly, the first term will be E naught times C naught square plus E1 times mod C1 square and so on, right. The first term in the expansion is same as this term. The second term, however, is different because here every time E naught comes. Second term, third term onwards, here it changes E1, E2 and so on. So, that is the difference. So, let us compare this term with this term. If you compare this term with this term, which is larger? This term, E1. Why? Because E1 is greater than E naught and mod C1 square is positive. Remember that positive is very important, otherwise the argument is not clear, correct. If I multiply a larger number by a positive number, then it remains larger by the same positive number, of course. So, each of this term, if I compare, this becomes larger than this, and hence I can say that the E naught is less than or equal to psi tilde A psi tilde. Is it clear, the proof? Or vice versa, whatever. The proof is very trivial. We have done this, but again it is very interesting proof, okay. And the proof does not require the normalization to be taken, but we have just assumed the normalization because of the simplification. Otherwise, this whole thing would have actually gone in the denominator. That is all. So, nothing would have happened. That denominator could have been multiplied with this E naught, because if this is there, then I can always say this is greater than or equal to E naught times psi tilde psi tilde. So, that is what I am proving. So, I hope you understand it does not matter. Then it would not have been 1, it would be actually psi tilde, which I can still multiply. So, I can show that this is greater than or equal to E naught times psi tilde, which is again the same, because this quantity is always positive. Okay, if I can ask you to prove without assumption of the normalization, all right, you should be able to prove that. Just a small quiz question. That same proof you repeat without normalization, then your proof will be this is greater than or equal to E naught mod Ci square, which is what I have shown. You are allowed to do that simply because this is always positive. I hope you know that the norm of a wave function must always be either 0 or positive. It can be negative. Okay, if it is negative, of course, the sign would have changed. I hope all of you know. This would have become less than equal to. So, it is positive. So, I have proved the same thing. So, the proof exactly goes in the same way. So, the normalization by itself is not really a big deal. It is just that it's easy to show. Okay. So, this actually gives you a very nice handle to apply the variation method, and this variation method has been applied in many cases. In fact, people have done particle, even single particle problems which are exactly solvable, you can do variation method. particle in a box, hydrogen atom, harmonic oscillator. Hydrogen atom, there are famous problems of variation method where you assume the wave function psi tilde to be of the type e to the minus r, but just say alpha r and vary alpha tilde. See what is the value of alpha you get. You know the value of alpha, so you will see what the value you get. Correct. So you can keep doing it. You can do for harmonic oscillator. You can take any part of the solution. Particle in a box. In fact, many times we used to give particle in a box as a variation method. You all know the solution, of course, but we can take a variation method like 0 to L. I can give you many such functions which is 0 at x equal to 0, 0 at x equal to L, and then find out the result. So one of them would be like x minus x into x minus L, x into x square into x minus L whole square, whatever, all powers. So a particle in a box variation method would be psi tilde as am mn amn x to the power m x minus L to the power n. It's a good solution. Yeah, I have given this problem, I think, in exam, but it's a good problem, a tough problem, lengthy problem, not tough. Conceptually very easy, but lengthy problem, and you can find out amn. So there is no sign here, just different way, and depending on how many terms in the expansion you take, your results will be as good as possible. So you can do it even for single particle problems which are exactly solvable, just to test the variation method. You don't have to do it, but just to test the variation method. But there are situations where many particle problems like helium atom, there is no option. In fact, we did also the helium atom variation method. You have to apply the variation method. So that is what we will do for all cases where variation is required, and in particular here we will apply the variation method in deriving the Hartree-Fock equation. So when I come to the Hartree-Fock, I will state that. So please remember the variation method. So